எங்க ஹெச்ஓடி மேம் இன்னும் வரணும்னு இங்கிலீஷ் என்ன சொல்லணும்?
என்னுடைய இமேஜ் தெரியுதுங்களா?
Sir, now we can see your screen only, sir.
Stanley?
Sir?
Hello?
Sir, good morning, sir. Stanley.
Sir, உங்க screen தெரியுது sir. Your screen is visible.
Image வரலைங்களா?
No, sir. Your screen only is visible. Hello, sir. ஸ்க்ரீன் ரெண்டு ஒரு திருப்பி முகத்துக்கு போடுறது என்ன பண்ணணும்னு கேட்டேன். ஒரு பேர்
மேம் சொல்லுங்க. வந்துட்டாரு. சொல்லிடுவோன்னு அவருக்கு தெரியல. ஓகே. ஆமா வராங்க மேம், வராங்க. அவர் வந்துட்டாரு திருப்பி நமக்கு.
இப்ப கேக்குதுங்களா?
Yes sir, you are audible only. Hello sir. Hello sir.
Okay. Okay ma'am.
ஸ்க்ரீன் போடுறது தெரியுமா?
வந்துட்டாங்களா?
Yes, Stanley?
Yeah, hello sir.
ஹலோ
ஐயா சார்.
இல்ல இப்ப இடையில கால் வந்துச்சுன்னா என்ன பண்றது?
கால்
கட் பண்ணி
நீங்க
விட்டுலாமா?
அட்டென்ட் பண்ண வேணாம் சார், கட் பண்ணி விட்டீங்கன்னா போதும்.
சரி.
இப்போ ஸ்லைட்ல இருந்து பேக் டு உங்களோட இமேஜ்க்கு போறதுக்கு பாத்தீங்களா சார்?
இல்ல வேண்டாம், ஸ்லைட் தெரிஞ்சா போதும் விடுங்க.
ஓகே ஃபைன் ஃபைன் சார். யா சார். சொல்லுங்க சார். தேங்க்யூ.
ஹலோ
ஹலோ சார்.
என்ன மேடம் எக்கோ வருது?
சார் ஒன் செகண்ட்.
மேடம் இட்ஸ் டைம் மேடம், வில் ஸ்டார்ட்.
Sir, 1 second, sir. Our HOD will come, sir.
Can you hear me?
Yeah, sir.
Yeah. It's time, madam. Shall we start?
Sir, 1 second. Our HOD ma'am will come, sir. Sir.
So she has not joined.
Yes, sir. Ma'am, 10 o'clock ஆயிடுச்சு. மேம் ஷார்ப்பா வந்துருவேன்னு சொன்னாங்க, வரல. ஓகே ஓகே மேம். இவர் எப்படி அவசரப்படுறாரு? ஆமா மேம். புதுசு போல இருக்கு. ஆமா, எக்ஸைட் ஆயிட்டாரு. ஓகே சரி மேம், அந்த ஒன்று ஸ்டார்ட் பண்ணிக்கலாம் மேம். கண்டிப்பா. ஆமா ஆமாங்க. சரி மேம், கால் பண்ணவா? வேண்டாம்ல. ஓகே 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 மேம். ஆமாங்க மேம். ஆமாங்க மேம். மேம் கண்டிப்பா வரேன்னு சொன்னாங்க. ம். மேம் இப்போ வந்தாச்சு மேம், வந்தாச்சு. ஒரு செகண்ட். ஹலோ மேம், குட் மார்னிங் மேம். Hello ma'am, good morning ma'am.
Good morning, shall we start?
Yes ma'am. Sir?
Yes.
Very good morning, madam. We will start now.
Yes, sir. Yes, sir. Respected Professor Dr. NJR Muniraj, organizers of this virtual meet, Ms. Shijita and Ms. Carolyn, dedicated faculty and very motivated student participants, good morning. Warm greetings from Avinasilingam Institute. Hearty welcome to all present in this meeting room. I bring good tidings from Department of Biomedical Instrumentation Engineering, School of Engineering. Avinasilingam Institute for Home Science and Higher Education for Women was the premier institution in South India to offer the 4-year BE degree program in Biomedical Instrumentation Engineering way back in 1996. We now offer ME Medical Electronics and PhD in Biomedical Instrumentation Engineering also. The department has very unique laboratories like Virtual Instrumentation Laboratory, Diagnostic and Therapeutic Equipment Laboratory, and Biosensors and Transducers Laboratory. We have also established a National Instruments Authorized LabVIEW Academy to provide training for students and faculty. The faculty are dedicated and involved in research funded by government agencies. I'm happy to welcome you all on behalf of Avinasilingam Institute. I'm honored to welcome our guest of honor, Dr. NJR Muniraj, to this virtual meet. It's my pleasure to introduce him to you. Dr. Muniraj, in the pinnacle of his career, is here with us to share his expertise on digital signal processing. He has a rich experience in teaching, spanning over 30 years in various educational institutions. He has also worked as a consultant in various industries. He has organized numerous conferences, FDPs, workshops, seminars, and symposiums. His paper publications in conferences and peer-reviewed journals exceed 125. In a nutshell, he's a good teacher, he's a good researcher, and a good leader. Sir, on behalf of the organizing committee, I welcome you once again. I welcome the faculty, the research scholars, PG and UG students who are participating in this session with enthusiasm. Thank you. The coordinators of the virtual seminar are Ms. Shijita and Ms. Carolyn. I appreciate their sincere efforts in organizing it. Over to you, Shijita, for the rest of the meeting. Thank you.
Thank you, ma'am. Very good morning to everyone. I hope it should be a great time to brush up the basic concepts of digital signal processing in biomedical engineering. Participants are requested to mute your audio and video to avoid disturbances during the session. You can post your questions in the chat box. At the end of the session, resource person will be answering your questions. Thank you for your response. Now, I request Honorable Resource Person to initiate the session. Sir.
A very good morning to one and all present here. It gives me a great pleasure to be here on presenting this webinar. I would like to thank the managing trustee of Avinasilingam and particularly the organizing secretary, Dr. Judith Justin, and the coordinators, Shijita and Caroline, for making this webinar a successful one. I am very happy to present this topic, digital signal processing, and particularly in biomedical engineering. Let me start with the Kural. கேடில் வெளிச்செல்வம் கல்வி ஒருவர்க்கு மாடல்ல மற்றையவை. It means learning is the best of all things. Other things are not at all important. கல்வியை தவிர இந்த உலகத்தில் சிறந்தது வேற செல்வமே இல்லை. This was told by திருவள்ளுவர் in திருக்குறள் before the birth of zero. And I'm sure DSP is one of the subject where if you strong in this subject, you can lead the world, you can lead your life in a better way, as I have seen so many students who take DSP as a prime subject. And I'm very happy. DSP leads the world. Everyone knows about DSP. So not only DSP is used in biomedical application, everywhere nowadays, without DSP, the life is not possible. And wherever we go, you can see a DSP. Everyone has a phone, a cell phone. There is a system on chip. And wherever you see anything, an LCD, a washing machine, a television, everywhere without DSP, it is not at all possible. And we have seen so many applications of DSP, and DSP is not a simple subject. Everyone afraid of studying DSP because of it is of mathematical equations. But one thing you have to remember, if you are strong in mathematics, you should study DSP because Now all biomedical applications are emerging from digital signal processing by means of VLSI technology. And I am going to say some challenges and opportunities and the history of DSP and the DSP design flow, how it is used in the real world. Now let us see the challenges and opportunities. So as per the report, it was seen that consumption for electronic equipment will grow to $300 billion by 2020. And there is an annual growth 30% in the Indian semiconductor and embedded system. And India's semiconductor is expected to touch $100 billion. And auto sector could grow to $245 billion, particularly because of semiconductor. That means DSP. India is one of the fastest growing electronics market in the world, and 100 billions of investments could happen in the next few years. And also we know a lot of foreign countries are going to set up industries in India, and particularly Cyprus is going to set up a lab in Coimbatore. A $1 billion company is going to be held at Coimbatore, where they are going to have a $1 billion company specifically for semiconductors. And also analog devices is planning from China to India. And most of them are now planning to Coimbatore because of it was very similar to Bangalore. So I request all the students to be a strong DSP and a VLSI engineer so that the life will be very smooth for them if they are strong in DSP. And the availability, if you see, there are around 950,000 educational institutions are there in India, and 194,000 number of students graduating every year, and 25% of them are only employable. So you can see this pathetic situation, and India needs well over 10,000 PhDs and twice as many master degree holders. And if you see, 120 semiconductor companies are there in India, out of which 80 in Bangalore. And each requires at least 3,000 engineers and 10,000 diploma holders on an average per year. And 2,400 engineers and 5,000 diploma holders in DSP and VLSI design alone in Bangalore per year is required. Only 10% of the graduating engineers are eligible, and these needs talent pool where engineers have. So the idea is there are a lot of openings, there are a lot of placements are available even in Bangalore for biomedical applications, particularly for these semiconductor industries in Bangalore. The thing is the knowledge in the subject and the software knowledge of DSP and the software knowledge of VLSI is very less. If you see, they study so many subjects, but they are not concentrating on subjects like DSP, VLSI, biomedical. See, biomedical is an application, but you should know how it is implemented. Only if you know certain concepts like DSP and VLSI, you can do innovations in biomedical. So that is my idea, and there are a lot of challenges for the students and for all others. And once if you concentrated more on DSP, I think life will be flying colors. And if you see the DSP history, see, just see how the history has started. See in 1906 how a filament, and Anderson has started is a filament and a transistor. Just see, and there are so many birth of modern electronics. You can see a transistor, you can see, you know, IC, you can see so many ICs, and first chip and processor. In 1985, in 1971, 85, it has 166 into 222 mil. That is the size of that 8085 processor. And 1 mil is equivalent to 1 by 1000 inch. That was the size of 85, which has 6,200 transistors. and it has 5 megahertz, up to 5 megahertz it can work, 3 to 5 megahertz it can work. Then came 86, where you can see with 23,000 transistors, and then came 286, 386, coprocessor, 486, 586, Pentium 1, etc., etc. Let us take one simple example, Pentium 4. Pentium 4, if you take the processor, the size of the processor is, if you keep an ant in front of that chip, the ant will be very big in size. ஒரு கட்டெரும்பை எடுத்து அந்த சிப்புக்கு மேல வச்சா the கட்டெரும்பு seems to be very big in size. Then see how the size of the chip, that is, it is millions of transistors, but the size is very less. One more medical application was there few years back. An Indian scientist has developed a medical chip with 50,000 billion transistors, which is also used for roam-free applications. And the 50,000 billion transistors was stored in a single hair width size. Or my இழையில், the 50,000 billion transistors were fabricated in a chip. So this clearly shows the technology is developing as per the Moore's law. So only thing, we have to develop ourselves to compete with DSP. So DSP is one of the processor like that. So like this, a DSP came, and now later on you can see system on chip and etc., etc. So what is DSP? DSP, suppose this is nothing but digital signal processing. And what is this digital signal processing? So you have a input signal. So it may be a voice signal, it may be an image, or it may be any signal. So normally digital signal is used only for signal processing. So there are a lot of signals, biomedical signals we have to process. ECG signal, EMG signal, EEG signal, EEG signal. Just a minute, I'll just open the screen. Is it okay now? It's clear? Screen is clear? Hello?
Sir, now only it's going to presenting, sir.
இல்ல ஸ்கிரீன் தெரியுதுங்களா?
Yes, sir.
We couldn't see your presentation, sir.
We can't see your presentation, sir.
Just a minute.
So now it's visible, sir.
Sir, please unmute your audio, sir.
பேர் போனா
Hello, sir.
Can you see me?
Yes, sir.
Can you see me?
Now it's open, sir.
Okay, but screen is not opening.
Yes, sir. Your screen we can see.
Just a minute. Here it is not opening. Hello.
Sir.
It's opening.
Yes, sir.
Can you see the same
But your
image
screen
is not there?
no, sir.
Just a minute. Okay.
Yes, sir.
Okay. So, DA, sorry for the disturbance. It was due to the technical problem, and hope you can bear the technical problem. So, DSP is very world famous, and you can see how the discrete signals are sampled. And there are a lot of other applications from DSP. So DSP is nothing but you have a signal, you convert that analog to digital by sample and holding, you process it, then you take the digital signal, you reconstruct the original signal. See, but it may be very easy, but this DSP has helped a lot in so many real-time applications. For example, see, from the basics, the DSP has emerged. So many signals are there, and DSP aims in lot of outputs, lot of processing tasks, and DSP is used for all processings like general purpose processors, FPGAs particularly, now FPGAs. If you know about FPGA, field programmable gate arrays, now FPGA has emerged, and that is another one special concept where field programmable analog arrays. So these DSP concepts can directly fitted into this FPGA and can be used for system on chip applications. And there are so many applications. This is the idea of a DSP. So you filter it, you convert the digital signal analog to digital, you process it, then again you reconstruct the digital signal and analog signal. And what is special in this DSP processor is you are reconstructing the signal without noise. That is the idea behind it. Okay. Suppose, for example, you could have heard about audio cassettes. During 10 to 15 years before, audio cassettes were very famous. And if you record that audio cassette, initially it was okay. But after some time, it has affected by so many noises, hum, hiss, scratch, white noise, Gaussian noise, and so many noises. But how to reconstruct the original signal? It is not possible. Few years before the development of DSP. Then after the development of DSP, even if it is 50% or less than 15%, you can reconstruct the original signal with the full effect. So that is the idea of the DSP. It was very, that period in the early stages, it was an exceptionally, everybody viewed it was a great innovation. Then came image also, same way. And suppose if you have an image, for example, suppose a photograph, a JPEG image, a photograph was taken by myself. Okay, and if you see my watch, okay, my watch will be a just dot. And if you enhance it, you can zoom it, okay, and you can see the timings, exact timings. That is DSP. So DSP, it reconstructs the original signal. And also it has given way to so many other applications like multi-rate signal processing. So in DSP, we do a sampling rate in constant sampling signals. But whereas in a multi-rate signal, the sampling rate will be different. So using the upsampling and downsampling method, decimation and interpolation method, we do multi-rate signal processing application. Later on, this application is used for medical field, and it was a boom for Coimbatore. Coimbatore was very famous for medical applications, medical transcriptions, and that is because of this multi-rate signal processing. How? For example, simple example, if you take normally in an MP3, normally an audio CD, if you take, it will be around some 12 songs. A very simple examples we'll take. 12 songs only can be stored and audio songs. But whereas if you take MP3, you can record more than 180 songs. So this clearly shows how to compress and how to decompress, how to decimate and how to interpolate. And this was the clear idea only after the development of multi-rate signal processing. And this was given a way to so many other applications like wavelet transform. So wavelet normally in FFT, if you take an FFT, so just I will go to the next slide. DFT. What is DFT? So DFT is a major tool in DSP where computations can be done. It was the first software tool developed by the industry, computer industry. So here, if you have 8 ECG samples, if you want to compute it, it takes 64 complex multiplications. So it takes huge time to process it. So they need a higher end of that. So they developed an FFT, fast Fourier transform. In DFT, it took n square complex multiplications to compute the sample. Whereas if you take FFT, it takes only n by 2 log to the base 2 into 2 power n. That is, if you have a n point transform, break the n point transform into 2 n by 2 point transform and 4 n by 4 transform and 8 n by 8 transform, and this process will continue until you get a single point transform. This is the idea. So based on this, data compression was developed where you have a real term and an imaginary term. Take the real part alone, and based on this compression idea, image compression was developed. So you take an image and it will be in the form of blocks. You take 2 blocks and you compress it, and the image will get compressed. And it was very famous, JPEG compression, during the medical applications. But the problem in that is the edges won't get compressed because it is in the form of block. The edges won't get compressed. So they need another concept where the edges also will get compressed. So then came wavelet transform, where it is represented by means of pixels. So since it was in the pixels, it was very easy. The edges is not there, so easily it was compressed, and the compression ratio has been improved, and the lossless medical compressions has improved a lot, and particularly the medical transcriptions boomed in Coimbatore because of these ideas. So the DSP has given a way for so many businesses in Coimbatore particularly, and it has boomed. Now, even now it is boom. Medical transcription is booming like anything because of wavelet transform. So what we do in wavelet transform image compression is, you take an image, you split that image into 2 images, low frequency components, high frequency components, approximate coefficients, detailed coefficients. Then again you break that into low, 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 high, high, low, high, high. So you take all the high, high frequencies. Again you take only the low, low. Again you split it into 2 hops, 4 hops, etc. So until you remove the high frequency components, you have to process this. This is one of the medical applications where medical transcription applications used in Coimbatore now, and it also boomed the industries. And FFT has become very famous on that. So it also used for so many other applications for spectral analysis, frequency response, convolution. You know convolution. Convolution is the mixing of 2 signals. So it converts the time domain into frequency domain. It's a mixture of 2 signals. And you know, very famous Kamala Hassan has introduced a song, Ruku Ruku. There is a song in Avai Shanmugi where convolution in FIR concept is being used. So every people will think that, oh, Kamala Hassan, he himself singing a song like a lady, old lady. It's not like that. So he sings as usual, and the sampling, frequency sampling method that into a lady voice. Likewise, you can do anything with the help of DSP, and it can be used for n number of applications everywhere. And if you take these DSP for design FIR, that is filter application, you know what is a filter. So filter concept is used for bandwidth designing. So if you want a good bandwidth, so if you want your internet to work properly, if you want your 2G, 3G, 4G, 5G spectrums, etc., everything should get properly done, then we need a filter, FIR filter. Properly it has to be designed. Not only this, later on this FIR filter was widely used for medical applications. Let me also give some 2 or 3 examples how these FIR filters are used for biomedical applications. So how to design this FIR filter is, you take the filter specification, you calculate the coefficient, you find the magnitude and phase spectrum, and you realize it, simulate it, and implement using hardware DSP processors. So this was the thing done in natural by using TMS processors, and also now analog processors are also there, which is widely used. And how these FIR filters used for is by means of VLSI. So you people, if you want to become a strong biomedical engineer, my special idea is, nobody is thinking of this. If you know DSP is okay, but how to implement these DSP application is a special tool. There is VLSI tools. There is one tool called Verilog HDL and a VHDL, and that is nothing but an ASIC implementation, application specific integration. That is, you simulate it, you synthesize it. This is the front end analysis. Then you floor plan, you route it and fuse it in the chip. This is the back end analysis. If you do this, and this application will be multiple times faster. If you do a process, same application in DSP, it takes 10 times means and faster. Then if you do it in the same application in VLSI, it will be 100 times faster. So that is the idea behind DSP and VLSI. That is why most of the application now they are developing by means of chip design, VLSI. Industries are taking so many applications of medical. So I will show some few examples. See here, a DSP 10 into more DSP throughput than DSP process, and this is cost effective, flexible hardware implementation, and this is a single chip. So that is why we go for VLSI in DSP applications. And you can see a simple application. See, if you take a programmable DSP for 1 gigahertz, it takes 1 gigahertz and 256 clock cycles. It takes 4 million samples per second. The same design, if you do it in VLSI, it takes only 500 million samples per second. This clearly shows how important the same DSP if it is applied in VLSI. So my dear students, you should concentrate more on DSP. At the same time, you should know VLSI, how it is implemented by means of that tool. Let me take a small medical application. We heard about heart transplantation. Heart transplantation in Texas University in US, this is specially designed for heart transplantation. Only medical hospital for heart transplantation is Texas Medical University. So here in this hospital, 50,000 people were waiting for this heart transplantation to get a new heart. You know that. And that too, and these operations are mostly, it is not successful. In Coimbatore, you would have heard about in few months before, there was a heart transplantation. Only one heart transplantation which was held at KMCH. And what is my idea is, so these heart transplantation can be done using DSP and VLSA. How? See, you have a old heart, and this old heart is problem. So, and you have a new heart. You suture the new heart over the old heart. Okay, and you compare the output. There will be an error, and you know the original output. You compare these two, and if you reduce this error, it becomes zero. It won't become zero. You won't get a global minima. You will get only the local minima as per the neural networks, and you can reduce the error by means of, we have discussed a lot of doctors and they told it is possible, and we also presented this concept at Bangkok and Japan, and it was accepted by so many doctors also. This VLSI chip where these operations will be done, and where we used is a FIR filter, where we has taken the algorithm is LMS, least mean square algorithm. It was clear that if you are very strong in the fundamental concepts of DSP, then I am sure a major operations like this will be helpful for the society and for your applications also. You can see the image where 2 hot signals, 4 down signals, it is processed in the DSP processor LMS hot signal, and it is reduced until you get the error gets reduced, the process will be done. And it's all done in a simple chip, very small, minute chip. Here the maximum frequency used is 100 megahertz, and the error is less than 3%. Number of iterations 100, and the technology is TSMC 130 nanometers. The data format is IEEE 754, and the filter order is 8th order FIR filter. It clearly shows that biomedical, if you want to be a very strong biomedical engineer, according to my view, you can be strong in any subject. You can be strong in any different subjects. But if you are strong in DSP and VLSA, I'm sure, like this, there are so many. One more application I would like to say, that is, heard about stethoscopes. So in stethoscopes, we can hear the ECG signal. The doctors will hear the ECG signal, and based on that ECG signal, the doctors will say this, will give the prescriptions will be done as per the stethoscope details, how they got. But history says, the literature survey says, if you hear the sound in the stethoscope, you won't get ECG signal alone. There is one more signal interfaced in the ECG signal, and that is nothing but a lung signal. So this lung sound and the heart sound will be interfaced together. Only an expert doctor, an experienced doctor will differentiate. This is lung problem, this is heart problem. And there is no device so far to differentiate this is a lung sound and this is a heart sound. And this is possible if you can do a lot of innovations in this. And now there was a device using MEMS, micro electromechanical systems, that is also fundamentally a VLSA and DSP device. And if you use this device, it can differentiate this is the lung sound and this is the heart sound. So you can simply, the doctors can easily identify this is the lung sound and this is the heart sound, and based on that they can analyze the body. And this is also a very big breakthrough in the medical history, how DSP is used. And also in FFT, if you see the MRI scanning, in MRI scanning, the radiations will be inside the human, the patient will suffer a lot of times. It has to be scanned using MRI. So that is around some 60,000 radiation pattern will be there, and which is more than compared to a washing machine radiation pattern. So if you use an FFT concept, where in the K-space, in the state space analysis, space domain analysis, if all these signals are there, it can be truncated to a single signal by means of fast Fourier transform. There are wide applications in biomedical, and there are a lot of innovations now getting implemented by so many students, particularly for corona. Now there was an innovation where how an electromagnetic radiation can be applied and it can suppress the corona. So likewise, so many other concepts are there used in biomedical applications. My dear students, this is a simple ideas what I have given using DSP. You can do a lot of innovations if you are very strong in FFT and filter concepts. And with one more Kural, I would like to end my talk. In Tirukural, it was clearly told that ஒருமைக்கண் தான் கற்ற கல்வி ஒருவருக்கு எழுமையும் ஏமா புடைத்து. Learning occurred in one birth will protect the individual for the next 7 birth. அதாவது நீ கற்ற கல்வி இந்த ஜென்மத்தில் மட்டுமல்ல 7 ஜென்மத்திற்கும் அது உன்னை மட்டுமல்ல உன்னை சார்ந்தவர்களையும் உன் பெற்றோர்களையும் காக்க வல்லதாக இருக்க வேண்டும். See how beautifully it was written before the birth of zero. That is the idea of the knowledge, that is the idea of the learning. So with this, let me ask my students, my participants, my faculty members, do concentrate more on DSP and you can be a successful engineer. And if you have any questions, you can ask. Thank you. Any questions? Hello? 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 Madam? Madam? Hello? Madam? Hello? Hello?
Sir?
Any questions?
Dear participants, if you have any questions, you can post it in the chat box, please.
Even if they want to ask I will give my phone number 9344707218. If you have any doubts regarding biomedical applications or tools or any other help, if you want, you can directly ask me. And my mail ID is njrmuniraj@yahoo.com. I'll be very happy to help all my co-friends, those who are particularly interested in signal processing and image processing and biomedical. I would like to thank the management and I would like to thank all the coordinators, particularly Stanley and Shijita and Caroline for arranging this webinar. And I will also thank Dr. Judith for giving a chance to discuss about DSP. Any questions? I am very happy to answer. If no more questions, shall I complete, madam?
Sir?
There is no more questions, shall we close?
One question from a participant, sir.
Yes, madam.
Explain the applications in mathematical modeling using DSP processor.
See, for example, if you take FIR, okay, see what FIR is defined by like this: y of n is equal to summation k is equal to 0 to n minus 1 x of n e power minus j omega n. This is the mathematical, very simple mathematics. But what is this? The present output depends on the past and present output. Based on this, you developed a structure, and based on that structure, you write a program and you do any applications based on that, you can do that.
Okay, sir. Thank you, sir. Someone asked, DSP project is based on software or hardware?
See, DSP project is basically a software. First, you should do the software, and it can be implemented for real-time application using hardware. Particularly if you go to VLSI instead of DSP, if you implement the algorithms of DSP in VLSI, it will be quite simple. The front end will be a simulation and the back end will be the hardware. Any other questions?
Sir, another question. Can you explain the major biomedical tool using DSP?
There are so many biomedical tools used. Okay, so what tool? Axon tool is there. I have used Axon tool, and I have used Cadence tools for biomedical applications. And there are n number of tools there are, and depending on the application. For example, if I use adaptive signal processing, I take an adaptive signal concept. There are a lot of tools. So there are n number of tools. Depending upon the application, you have to select the tools and you have to use it.
Okay, sir. Thank you, sir. Another question. Can we check the results in medical applications?
Sure, of course. See, for that, you can check you can take the samples. For example, I told about that comparison of these signals. Okay, you take two ECG signals and you simulate it and you check the timing diagram where you can see the simulation output, where you can see the difference, whether error is getting reduced or not. Then you can apply a neural network, you can train it. It is easy.
Okay, sir. Sir, any
Yes,
open
madam.
source software to learn DSP and simulate by ourselves? Someone asked this question.
Any?
Open source software to learn DSP.
See, nowadays we are using only open source, all are free version softwares. We are not going for any cost-effective softwares. All are open source softwares we are using. See, I told you, see, there is, for example, LMS. If I do an heart transplantation, I need an LMS. So specifically an LMS open source software is there. So you take that software and you do that. Similarly, depending upon the application, n number of open source softwares are available.
Okay, sir. Thank you, sir. Another question. In software, if we write a code to process a signal, what if it is for ECG equipment and how do you connect it?
See, for example, ECG signal, first we have to convert that into the IEEE format, floating point. Then it will be stored in the as a signal, digit zeros and ones. Then you can process it. You take the ECG signal, convert that into an using IEEE format into a floating point. Then it will be in the form of zeros and ones. Then you can take that as an input and you process it.
Okay, sir. Thank you, sir. Another question. What are the DSP gadgets used for monitor physical characteristics of the body?
See, now even for if you take a COVID, the sensors are there to directly monitor. The sensors is directly you can see the temperature, and you can also see the heart problems without going to any hospital or doctors. Like that, there are so many gadgets available. And for COVID, it has been widely used in Wuhan, a sensor device where the name of the device I've forgotten. That is a type of sensor. If you keep it in the below the arm, it will show the temperature and also it will show you the ECG signal. Like that, there are so many gadgets are available.
Okay, sir. Thank you.
Thank you, madam. Thank you, madam. Yes, any last question? Yes.
One more question, sir. Last question. How the human body signal is observed and given to the DSP processor?
See, this first we have to analyze a lot, and then based on some physiological analysis, then only it will be done by the biotechnology student. First, we have to do ourselves. and then the doctors will take care of that. For example, if we analyze that heart transplantation signals ECG, so first it has been done by us and it has been explained to the doctors, and then it will be directly taken as a zeros and ones, because now the real-time signals can be given to us like endoscope and all. So it likewise it is given.
Okay, sir. Thank you, sir. One more question. Can you be able to,
Yes.
can you explain how the EMG is getting better by DSP to differentiate the signal other body signals?
EMG is electromyograph, okay, whereas
Yes, sir.
muscle contraction will be done. So here the DSP is one more type of application where I told you already. So the DSP is the best thing, okay, where you can reconstruct all the points without, it won't take even, the error will not be there. That is the idea. So that is why if you use DSP, it becomes the better output. You can take the better output compared to other devices.
Okay, sir. Thank you, sir. Can you
Thank
repeat
you.
your contact number, sir, please?
9344 70
344
70 7218. And in IISc, madam, in IISc, there is a DSP man, and there is a DSP lab, a real lab. And students, if those who are interested really, first they have to give an idea, and based on that idea, present there, they can do their work in the DSP lab, so with DSP lab. And also in building companies, there is a biomedical lab. They have developed a MEMS lab. So you can go there and you can utilize all these facilities. India is doing a lot for biomedical applications now.
Okay, sir.
Thank you, madam. Thanks.
Okay, sir. Thank you very much for taking the time out of your busy schedule, sir. Thank you so much for your outstanding presentation in DSP. And your years of research and depth of understanding triggered our interest and knowledge towards DSP, sir. Thank you very much. And I also thank all the higher authorities of our institution for encouraging us to conduct this kind of webinars. I also offer my humble gratitude to the head of the department, Dr. Jude Justin, for motivating and supporting us to conduct this virtual meet successfully. I thank my dear coordinator, Mrs. Sujita ma'am, for her profound endeavor towards this webinar. And above all, I thank all the participants for your kind cooperations. And we treasure your participations. Thank you for joining us. Thank you very much, sir. Thank you very much once again.
Thank you, madam. Thank you. It's my pleasure. Thank you.
Thank you, sir.
Thank you, Sujita.
Thank you, sir. Thank you so much for your wonderful
Thank
cooperation.
you. Thank you. Bye.
Sir, thank you so much.
Thank you,
It's a great session
Stanley.
for us.
Thank you, Stanley.
Yeah, definitely, sir. It's a great session for us. Thank you, sir.
Thank you. Thank you. Bye. Bye. Bye.
We end the session.